Okay. Good. So let's recap a little bit how we will work using state space models in state space form using the package class. But I have to say that we're using this package, but most other packages will have a similar way of working. Actually, class will help us to save some of the stupid work, so the boring work. While in other software, you have to design your own matrices of the state form and then pass it to the estimation and the filtering and the smoothing and so on. So first of all, as I told you, we have to take a model. And of course, in this part of the lessons, we will work with this class of models, the so-called unobserved component models. But any model, you can take also a RIMA, whatever model you have in mind that can be cast in state space form. So you first take the model, and it's not working, model. And you have to cast this in state space form, at least mentally, okay? And then, of course, from the coding point of view. Then usually this state space form will have some unknown parameters. Please, make in your mind a difference between the unobserved components or the state vector, which are, you can see them also as unobserved parameters, but we see them as like unknown processes, and we have to estimate them using the data we see. And the other parameters that are like, sometimes call them like super parameters, meaning that without knowing them, even the state space form wouldn't be completed. Okay, for example, if you want to put an ARIMA in state space form, of course, all the phi's and all the theta parameters and the sigma square, so the variance of the white noise, they are all parameters that have to be estimated, okay? And actually, we really don't have in the ARIMA modeling really unobserved components. Yeah, we have to play around with the state vector, but they're really not unobservable. They are connected in some way to direct it to the observable time series. But we will see in an observed component, we will have like a component for the trend, one for the, I don't know, business cycle, one or more than one for the seasonal components. That can be more than one, and so on. And in that case, we will distinguish the component itself, which will be part of the state vector, and that will be estimated using the Kalman filter and smoother. And the hyperparameters in that case will be, you will see, mainly variances, okay, that will govern how quickly these components can evolve over time. And sometimes even parameters like more like the ARMA example, okay? But anyway, so this model, cast in state space form, will depend on some set of parameters that I call theta, so this is a vector of parameters. And then, of course, we have to draw some kind of estimation of these parameters. We do that by Gaussian maximum likelihood, which is the thing that is easy to implement in the state space form. And okay, we're using the so-called linear and Gaussian state space. We're using a linear state space form, but then we will assume Gaussianity to estimate the parameters. State space models can be more general than this. You can have also nonlinear state space model or non-Gaussian, but things complicate a lot if you go in that direction. You have to solve the problem a lot by using a simulation, usually like either Markov chain Monte Carlo. I don't know if you ever heard that, Markov chain Monte Carlo methods, or something called particle filtering and that stuff. So if we go outside of the linear and Gaussian realm, then things get more complicated, and we'll be staying only on the linear and Gaussian parts of the problem, because everything works fine. So this state space form will have some unknown parameters. In particular, in class, we have to design, we call something, yeah, we call it the update function, which takes the model, takes the parameters, and it returns the model with the parameters in the right places, okay? So here, of course, we take the parameters theta. I don't know, they are just variances. Okay, I will write those variances inside the Q and the H matrix. In the ARMA models, I should put in the T matrix the theta, or actually the phi, and in zeta matrix the thetas, and so on. So whatever, so I decide the structure of the state space form, and then I am the one that decides the order of the theta parameters, and then have to say, okay, this is the variance of the white noise, and so I just assign that variance to the white noise inside this function. This is, and then you return the same model, so the state space object, whatever. And this is needed because we don't have to call ourselves the so-called optim function in R, so the optimizer. There is in class a function called fit SSM. Actually, yeah, in the language of class, it's more state space mod. So it's called in SSM. So fit SSM is the function that takes well, the model. And the model can have some missing parameters. Initial values for the thetas. So this is like the theta 0. You know, when we do numerical optimization, we always need to start from some values, and then the optimizer try to climb, if it's maximizer, up or down if it's a minimizer, and then we have to. So this is going to be the theta 0, and then we have to pass the so-called update function. What happens inside here, we don't have to care about what happened, but I explained it to you. Well, it just called optim. Inside optim, there is like a function. So the objective function is just calling the log-lick, so it's computing the log likelihood on the given model with a given parameter. So the parameters that the optimizer is trying to optimize, okay? And of course, it's trying to maximize the log likelihood. Actually, it's trying to minimize the minus the log likelihood, which is just the same thing, okay? So in some, I think I made an example. I made some notes on how to use fast. I think 3 different, yeah, a sequence of 3 lessons I've written, and you can find it in the e-learning. I think in the first one, I'm also showing you how to directly do this part. But in general, we don't need to do that. The fit SSM function will do this for us, okay? And so finally, we get here with some estimated known parameters, and of course, an estimated state space model, which now depends on estimated parameters. And with this complete state space model, I mean complete because we set all the parameters a number, we can carry out the Kalman filter, the smoother, the prediction, whatever we want to forecast. The prediction is more general. Forecast is like prediction into the future. Okay. So this is basically how we work with these things. As I told you, missing values are really not an issue in modeling state space form. And that means that, okay, there is like a predict function. You know, in R, the generic function to do any kind of prediction is predict. You have predict for regression, you have predict for all the machine learning models, probably you saw that. And there is of course a predictor for an object in SSM form. However, you may also just put the final Y, so the data, the time series, you can put them to missing. And in a natural way, when we pass the common filter and smoother, when he finds missing observation, well, he just will project the missing on the non-missing. Okay, so actually we could use the predict function, but you could just estimate an SS model on your time series when you leave some missing observation at the end, and they will be forecast automatically by the system, because if he finds them missing, I mean, that's not a problem. There are just data that he has to take care of, and will forecast the state variables. And if we forecast the state variable, we can also forecast the Y. Everything will be clear later. So we have two alternatives to do prediction. Yeah, sometimes it's simpler, the missing observation way to predict. And so we just keep the predict part. And then there's also some tools we will see to do some diagnostic check of our model. For example, it's very simple in this form, for example, to spot out like outliers. And the outliers will be interesting because the system will help us to identify not only the single additive outlier. So you may think a time series which is very regular, then it comes a single point which is out of the core, and that's an outlier, so an additive outlier. You could see as an extreme observation on the epsilon noise. Okay, but then you could also notice like a abrupt change in the trend, so a sudden jump in the trend. That's not an additive outlier, but we can spot also such kind of changes into the data by looking at some diagnostic checks that we will produce using the tools like FastGLS. So as I told you, the nice thing about this world, even though we haven't explored this world much yet, is that everything is included in the package, meaning we don't have to care about missing observation before modeling, as in many other models. So imputing missing observations is something you usually do before modeling. Here, it's not a problem. We will allow missing observations. We have a way to deal with forecast, but also to extract components from the data. So extract some information from the data, and we don't have to do that in a different framework than the same framework where we forecast. And yeah, outliers we can find, or structural break we can find using the tool. So it's kind of a word that it's all included. Okay, and that's probably a good for you. It would be a good idea actually. Instead of starting, usually when you do your project, you start from the ARIMA and then you go UCM and then machine learning. But probably if you start with UCM, you also solve some problem that you would find by working with ARIMA, and even more with machine learning. For example, the missing observation problem. Even though I didn't give you a time series with missing observations, so it's not a problem for this year. Anyway, so this is the way we are going to work. So before putting the hands on R and FAS, I want to just introduce maybe one or two of the components, just because you're quicker to understand at the beginning of the lesson, and then we will go on doing some application afterwards. So let's start with the first component, so the trend, or yeah, the trend. So that's how I rationalized the way to build components in UCM. Unobserved component models sometimes are also called structural time series models, but this is more an older name. So let's say the first famous book that kind of gave you all the tools to work with these models is a book by Harvey, which is an econometrician from Cambridge, and it's dated 89. So, and in this time they were called structural time series models, but then they mostly changed the name to an unobserved component model, whatever. But then there's been, especially during the 90s, but also the 2000 advancements. Anyway, so as I rationalize, so by looking for a long time to how time series, UCM are built, I kind of rationalize how they are born. So I will try to explain to you. Maybe it's easier to understand why they work the way they work. So in my head, you start from a deterministic function, and then you try to make that deterministic function stochastic. Okay, simple. But how do you make it? Well, first of all, that function, you can write a function using its like formula, f of x or whatever. But you can also describe a function in some way using its increments, okay? So if you're in the continuous realm, you would have like differential equations. If we are in the discrete, as we are, x, so in our case is the time, so the time that counts, 1, 2, 3, 4, and so on. We can describe the same function by describing the increments, the finite increments, okay? And that's how we build the trend. So what function can we use for defining the trend? Well, a straight line, why not? So the idea, let's start with the formula. I already give you some notation. We will call the trend mu. And of course, so this would be the intercept. I call it mu 0 because the intercept is the value of the function at 0. So we can, instead of calling alpha, we can call it mu 0, and it's fine. And then we have like the slope times the time. Okay, so this is just a straight line. How do we make it stochastic? Some of you may think, yeah, okay. Well, just a name for the intercept. You could call it alpha, but what's an intercept? Is the value of the function when x is equal to 0. So let's call it mu 0. That's also an intuition that usually it's not in our head. What's the intercept? It's just the value of the function when the x is 0. So why not call it mu 0? You can call it alpha if you want. Let's call it alpha, whatever you want. So this is more familiar, maybe. So this is a straight line. Remember that p is integer, actually, or if you want to be serious, it belongs to the integer number. So positive or negative. We actually take just 0 and the positive because it's good to do so, but it could be any integer point. So the point is, how would you make this stochastic? So do you have any idea? I mean, you can say, I just sum some noise. I can sum some noise, but I have something deterministic with some noise. I didn't make this component stochastic. What I mean by stochastic, I mean that it can evolve over time. It's not always the same straight line that I want. I want a trend that in some way is adapting to the last observation, to the newest observations. Well, yeah, the slope could be stochastic as well. And that would be the second. So you started from the second step, which is fine. We can make this. I mean, we can start or even doing that. We could start with a beta being stochastic, but I'll actually also the alpha could be made stochastic, meaning that, as I told you, I rationalized this by looking at this model in many years. I rationalized it always works like this. We have to rewrite this as a incremental equation. So instead of saying mu t is equal to something of t, we will just write mu at today, mu at time t is equal to mu at time yesterday, so t minus 1, plus something. We can write that. We can do that. I know if we were in continuous time, that would be like a differential equation. Say, okay, the increment depends on, but we are in finite time, which makes things easier usually. And we can say, okay, we can rewrite this as mu t equal to mu t minus 1 plus beta. And of course, as I told you, I need a starting value because this is an increment. So we're just defining today as a function of yesterday, but I need, so any initial value would be good, but I have an initial value when t is equal to 0, this must be equal to alpha. So I have to supply also this second information, which is, that's why I called mu, mu 0. The intercept, we call it mu 0, and it's equal to alpha, okay? So this pair of equation is actually equivalent to this one. And if you don't believe me, you just substitute this one into here, and you see that the equality holds. But I mean, it's very intuitive. What's the slope? Well, the slope is just the increment over an interval of 1, okay? So that's the definition of slope. And so we just rewritten the same object in incremental form. I call it in incremental form. How do we make this stochastic? Well, we can put some noise here. I call eta. So, well, this is a white. How do we interpret this? It's like the value of today is in part predictable because it's the value of yesterday plus a fixed slope. But then I add also a random component, a random noise. And so the slope will not always be equal to beta, but it will be, the expectation will be beta. But sometimes it will be larger and sometimes it will be smaller. And from an interpretational point of view, you can see this as a straight line that jumps up and down, okay? Because of eta. So there is a fixed slope, but sometimes the straight line, the slope is fixed. It's like an intercept in some way that is jumping up and down. This is actually, you already know this object here. You have a name for this? It's a random walk with a drift. So beta here is the drift. So if you remember, we already decomposed the random walk with drift. It's like having a deterministic trend, which is a line, a straight line, plus a random walk, a pure random walk, which is a non-stationary process. So it's like having, you can see it as the intercept of being a random walk. It just changes over time. So I can jump up and down, but the slope is always there, it doesn't change. So my prediction, if I observe this in time, of course I see this straight line jumping up and down, but my prediction will be just the last value of mu that I observed, plus h, where h is the horizon of the prediction, times beta, okay? I'll just use the same slope for my prediction. And as I told you, this you already know, it's a random walk with the grid. So actually, it's an I1 process, if you remember. So it's integrated over the way. But as he mentioned, I think, we could also make the slope change over time. So now we have the intercept that jumps up and down, but also the slope can change over time. Suppose we want to use this trend to model, I don't know, the GDP of Italy. I always do these examples because I guess everybody knows a little bit about the economy of his own country. If we go back to like the 50s or the 60s, it was an Italian miracle, so-called Italian miracle. We were increasing the GDP like China is doing now, so about 8%, 10% per year, okay? So the trend as well, usually, for example, we work on log of GDP. If we work on the log of GDP, this becomes the rate, the rate of increment. Okay? So this would be about, as I told you, 10%. And now the GDP, we're very happy if it grows by less than 1%. Okay. So now this would be about 1%. So we want a model where also the slope can change over time. And how to do that? Well, the slope is now a constant. We can write the constant also as a as an incremental form. So we can add. So we can put a t here. Usually we want to have the same t here. Actually, in our case, we also put the. Usually, as I told you, when we cast everything in state space form, we want the right-hand side to have all the same t's, and which are smaller or the one on the left-hand side. So we can also define. So this is the incremental form of a constant. It's easy. It's a constant is a constant. So the value of today is equal to the value of yesterday. So this is the incremental form for a constant. And so we just need to add some white noise, which I call zeta here. Okay. Hmm?
Can you see the behavior of the second sample?
Yeah. We'll go now on to R. Yeah, we will simulate some of these objects in R. Yeah, we did that for the ARIMA. We're going to do this here. So I think it's always good to visualize these things because it helps you understand how the values of the variance, for example, relate. And if this kind of trend, for example, is good for your time series you want to model. Yeah.
How the ability of capture the trend change when we make the data.
Yeah, of course. Now, this is not a random walk with drift. So it's actually, if you look at, this is a random walk. Okay. And here you see this is the integration. As you remember, I defined the integration as this process. So we're integrating this object here. And this is a I1 object because it's a random walk. Well, this is stationary. But this dominates. I never proved that to you, but you kind of have an intuition. Of course, an integrated process is a process that moves a lot, okay? It tends to go up and down without limits, I would say, okay? So if I sum an integrated process to a stationary process, which instead is a process that stays around a mean, a fixed mean, of course, the integrated process in some way dominates in the long run. So actually, if I sum an integrated process with a stationary process, I get an integrated process. Okay? I mean, these are just things we said for the ARIMA, so that's why I'm explaining it to you. It's not, at the end of the day, that relevant for an observed component model. But just to tell you that now that we made this choice, this is an I2 process, okay? And before moving to doing some examples in R and looking at different samples of these sample paths, I'll just make you notice some special cases. So just to be clear, this is what we are talking about. Let's write it already in state space form as we are used to. Well, this is already in some way in state space form. Okay. Actually, I write it in columns so it's clear for you. Put them in matrices. Okay. So this is usually called the slope equation. This is the level. Okay. And these two here are white noises. Okay. And we are assuming they are not correlated. We could actually assume they are correlated, but usually it's simpler. We have one less parameter to estimate if we assume that they are not correlated. In some way, zeta is responsible to making the slope evolve over time. If zeta is 0, the slope doesn't change. So if the variance of zeta is 0, the slope doesn't change. And if zeta is close to 0, it changes, but very slowly. The larger zeta, the quicker the slope evolves over time. And in some way, eta instead is the possibility to jump up and down for the straight line. And so the larger eta, the larger the jumps, the smaller eta, the smaller the jumps, okay, up and down. So one is up and down, and the other one is more steep or less steep, okay? These are the two movements we are allowing. And so we have, for example, if both variances are 0, so what do we get if we put both variances equal to 0? A straight line. So it's deterministic linear trend. What if I put zeta, just zeta equal to 0? Well, we have the random walk with drift. So it's a random walk with drift. What if I put this variance equal to 0, but also beta 1 or beta 0, whatever you want to call it? So the first observation. Well, this is just a random walk because I'm telling the model the slope is not changing and the slope is equal to 0. So at the beginning it was 0, but it's not changing, so it remains 0. So as you see, we get many particular cases that we already have seen in some way. What happens if instead sigma eta is equal to 0, but not the zeta? Well, we get the integration of a random walk, because beta is a random walk. We have no eta, because if the variance of eta is 0, then we are integrating a random walk. The effect, I think we already simulated that. It's a very smooth trend. Indeed, this is usually called either integrated random walk or smooth trend. Okay. Yeah, this is basically the interesting cases we can analyze. So actually, this is a stochastic trend. We can think as a locally linear trend. So it's like a trend that evolves over time. I don't know if we have to, like, this is our time series. Like, this is like the Italian GDP. So it starts good, it starts growing up, but then it kind of level out. So it's like we're having a set of different lines here. It's not changing much, then here starts changing. And of course, the prediction will be a straight line. And it's a straight line where this starts from the last observation, and it just sums. So this is n. So the last observation, if it's n, this will be, the trend will be mu n. And the predictions, I don't know, here, after h times will be mu n plus the last version of the slope times h. Okay, so this would be the prediction. It's like it's a slope. It's just a straight line, and we are exploiting the very last straight line to do the prediction. Okay, this is the best intuition I can give you for this object here. Of course, now we can simulate. It's simple. I mean, you can compute the conditional expectation of these two given today, and you will notice, well, this is a random walk, so the conditional expectation of the future of beta is just the last beta, okay? And this is the expectation of the future of this, well, it's conditional on the past. The past is made up of these two things. And of course, I just have to, so this is the slope. So this is the slope of a straight line. So if I go h steps ahead, I have to sum up h beta, okay? And I will be using the last version of beta. So I'm just using the last estimated straight line to predict the future. But the line is moving over time, okay? Yeah, it's a good idea actually to simulate a little bit from this so you can get a flavor from how the trend looks. We kind of did the same thing at the beginning of this course. So maybe we could write a function that takes initial values for mu and beta, the variance of eta, the variance of zeta, and we can try to play around with that. So we can, I don't know, in R, usually the function that generate random things start with R. This is called, sorry, I didn't give you a name for this object here. This is called the local linear trend. I mean, the name resembles what it actually is. It's just a local trend, local linear trend that change over time. Local because it changes over time. So in the short run, linearity is a very good prediction. Of course, in the long run, we will have larger and larger prediction errors, of course. And in some way, it's close to analysis because we know that everything that is moved in a local area is linear. So in the neighborhood of every point, we can approximate any continuous function using a linear function. So it's kind of the same thing here. So we can call it RLLT to generate sample paths from the local linear trend. Secondo me a casa sentono quantità di rumore. Ecco. È impazzito. È ufficialmente impazzito. Perché non funziona niente? Dai, non abbandonarmi adesso. Non mi mostra nessuno. Ah no, questo me lo mostra ma non lo volevo. Vediamo se adesso funziona. No, basta. Proviamo altre cose. Mi sta abbandonando. Provo con i tasti, vediamo se funziona. Non so cosa sta succedendo, non mi sta mostrando nulla di quello che voglio mostrare. Ah, ecco, adesso è arrivato. Okay, so RLT. So we want n, the length of the time series we want to simulate. So n is the length. Then I told you we want the two variances, so sigma, maybe the standard deviations, of course. So sigma eta and sigma zeta. And then we want the starting value for the mu, which we could, I don't know, mu0 or mu1. And the value for beta. We can use for loops just because it makes things more readable in this. It makes things very similar to what we write here and what we have written in on the notebook here. But anyway, nobody would use that because you know the for loops are very inefficient in interpreter language. But anyway, we will use that because it makes things simpler to read. So we need actually two time series. One is beta and one is mu. So we could already build a matrix. I don't know. We can just call this X. This is going to be a matrix where we want to put of 0. We can start with a matrix of 0, and we want n rows and 2 columns. Actually, we can even put the name. Maybe let's call beta. Well, the rows, we don't want names for the rows, but we want names for the columns. Okay. So this is just an empty matrix. Of course, we can start by putting, for example, the starting value for mu, which is mu1. We can start by putting the starting value for beta, which is beta1. Okay. And then, as I told you, I wouldn't use this in real life, but we can start, we can use the for loop. Of course, this has to run from 2 to n. Okay. Sorry, I forgot an in. And here we can write so we better start with the beta. So the beta of today is equal to the beta of yesterday plus a random noise. Maybe we can generate the noise before. That's simpler. I would say we add maybe I don't know. We can also build a matrix that we call white noise. It's n. Well, actually, it would be sufficient n minus 1, but anyway, let's build it n times 2. And again, we can give names here. The rows have no name, but the columns, we can call them, so eta and zeta. So everything resamples exactly the formulas that I have written. And then we can generate all at once all the white noises. We can generate, for example, the whole white noise for eta. So, and we generate n numbers from a normal distribution, and the standard deviation has to be equal to the sigma of eta. And we do the same thing with the zeta. Okay, so I already prepared. So this is like a blanket, a white blanket that we will fill up with the values of mu and beta. This is already filled up with a random white noise. Of course, we can generate them all at once because they're all independent, random Gaussian variates. And so here we can just call like t minus 1 eta. No, this is beta, so zeta. And here, so this is just a random walk. You see it from here. Okay, but mu is not only a random walk; it's a random walk with a moving drift in some way. So I will have x t minus 1 of mu, but I also have plus x t minus 1 of beta. And then I have the white noise. I go in the next line so you can read. Okay, this is the closest thing I could think of writing the code in a way that is very close to how we wrote the formulas on paper. If I can put some. Okay, so actually the local linear trend, we are interested just in the mu part, but I return both of them because we can kind of understand more things by looking at the pair. So if I didn't make any, well, I made some mistake because I already have, sorry, I have to define the function, sorry. So this is how it works in R. Sorry about that. Okay, now we can just experiment. We can just call R LLT. We will put some different set of parameters, and then we pass this. We transform this into a time series object. So when we do the plot, we have two plots, one for mu and one for beta. So, for example, let's start looking at, I don't know, a time series of n equal to 200. Let's start with sigma eta. Well, let's start with sigma eta equal to 1, maybe. Sigma zeta equal to 0.1. And then as starting values, we can select mu1 equals, I don't know, 100, and beta 1 equal, this is the slope, so maybe we can start the slope like it's an increasing straight line, okay? If it's positive, of course, at the beginning, the line is increasing. But then it will change because of the effect of this variance here, okay? Let's just check it. I want to leave more space for the plot. Okay, so this is the trend, mu. So this is actually what we kind of observe. This is just like a building block to build this trend here, this level. So we have a slope that starts from 1. Of course, anybody of you has a different picture because it's random. But I mean, the smoothness of this one will be probably similar for all the cases. So we have a beta. In my case, everybody is starting from 1 because we set the initial value equal to 1 of the beta. And then it moves. In my case, it's kind of stay around 1 for a while, and then it jumps up to more than 2, okay? And indeed, I see, and of course, I have to integrate this, and I integrate also a white noise component, but this is clearly dominating in this case. Indeed, in my picture, as I told you, your picture will be different. We have almost a straight line here because it stays around 1. It goes, yeah, it decreases a little bit. So, but it grows by 1 circa for a while, and then here it starts increasing more. And you see this, the slope of this line is changing, okay? But it's very smooth. Of course, if I want a more jumpy, a more abrupt trend, I have to increase the variance of eta. So if I put, for example, the variance of eta equal to 3, maybe I can set a seed so we can kind of see the changes for our, just due to our choices. Right, I regenerate this. Well, it doesn't change much. Strange, it's kind of the same. But anyway, if I set that equal to 3, then I will expect a much more noisy trend here because I gave more space to the eta shocks. So the one that are making our trend jump up and down. And you see, now it's much more noisy. And in my case, for example, that first it starts from 1. Actually, also your case, if you selected the same seed, then it goes negative. And indeed, we have first of all, we see a trend that goes up, but then also goes down because this turns negative. And so the slope is negative and it goes down. And then it turns back positive, the slope. And so we see again an increasing trend, okay? But you see, it's much more noisy because we gave much more a higher variance of eta. If we set the variance of eta equal to 0, then the trend will be very, very smooth. It's the so-called integrated random walk or smooth trend, okay? So it's very smooth. The only change, it cannot jump. You can visualize this. The trend can only change because the slope changes. So it cannot jump up and down. It can just slowly go down and go up. You may think, as I told you in other places, integration is a smoothing operation. The more you integrate, the more you smooth. In this case, we are just integrated something that is already integrated. So we get something very smooth. There is now the second effect of the stationary variable, which is gets integrated, which is less smooth. So that will be the responsible for the abrupt changes, and the integrated random walk is much smoother. If we do the opposite, if we set sigma zeta equal to 0 and sigma eta equal, for example, to 2, so what we expect, what do you expect? What do we get? So we set eta equal to 2, but zeta equal to 0. So the slope is not changing, okay? So this is just a random walk with drift. What's a random walk with drift? Well, it's something that tends to grow at in this case, at rate 1. So every time it increases by 1, but then there's also a random walk that makes this thing more noisy. You know, this is the slope. It stays 1. The average increase here is 1, but we also have a random walk component that makes this not exactly growing at the pace of 1, okay? And the more you increase the variance of eta, the less you see the drift. So for example, if I put the variance of eta equal to 5, probably we will not see the drift much. Well, we still see it actually, probably because 1, it's a strong drift. But I don't know, if I put it equal to 20, of course, we will not notice any drift anymore. Okay. but still is drifting. And then, of course, if we put all the variances equal to 0, well, then we have a straight line. All the variances equal to 0. We have a straight line starting from 100, so from mu1 or mu0, whatever you want to call it. I call it mu1 because our indexes start from 1. It doesn't really change, okay? And if beta is equal to 1, so it's increasing. Of course, this is just a straight line, and this is the almost the intercept because it's not 0, but anyway. If I put this minus 0.2, this is, of course, decreasing. It's just a straight line, okay? So we have many possibilities using this object. As I told you, if we want smooth trends, this is the way to go. Okay, as I told you, this is local linear trend. So this is linear locally, but then it changes. Local linear trend. And of course, what are the parameters to estimate using maximum likelihood? Well, sigma eta and sigma zeta. Okay, we have two variances that we have to estimate. The initial values, well, that's the duty of the Kalman filter and smoother that have to estimate the starting values. So for the filter, actually, we're providing a starting distribution for mu and beta. But as I told you, if we know nothing about the starting value of the trend, we can put an infinite variance and an arbitrary mean, meaning that we are not communicating any information about the starting value of mu and beta, okay? So these are both, they're non-stationary components. Beta is random walk, so it's non-stationary. Mu is the integration of a random walk plus something stationary, so it's even less stationary. So these two components are non-stationary. So unless I know better, because from my knowledge, I can give better information about the starting values, otherwise we set the starting values inside the state space form for mu and for beta with infinite variance, so diffuse initial condition, and we're just communicating our full ignorance about the starting values. The Kalman filter works forward, so start for a very uncertain starting point, and so we will have at the beginning of the Kalman filter very bad estimation of the trends because it starts with an infinite variance. Okay, then it observes one observation, but it's just one observation, and has to estimate the level and the slope. Will be, of course, no more infinite. Actually, it takes 2 steps to get finite, the variance of the filter, and then, of course, we will converge to a good, a reasonable estimate of the trend. The smoother, on the other way, it's working both backward and forward. So actually, the estimate of the initial value due to the smoother will be much more precise because it will use also future data to estimate the initial value for mu1 and beta1, okay? But we will see that. So let's start with, as I told you, probably an unusual example as far as forecast. So now this is mostly, it's called streaming data analysis. Actually, what we're doing with the example I presented yesterday, the one for the pole of poles example, or yesterday, last lesson, is a real-time evaluation of like poles. So it's like a streaming data problem. I don't see the student that had this problem with streaming in the first lessons. As I told you, the Kalman filter is something that works in real time, so it's good for streaming, okay, streaming data. There's only one problem. Of course, we always have, or almost always have, to estimate these variances. And these variances need some data to be estimated. unless if I have no info, I mean, if I'm starting with a new time series and I have no idea what these variances are, I just fix some initial value for the variances, and as soon as I've collected some data, I can estimate this variance. Of course, nothing can work with no initial observation. I mean, we can push something to work using initial observation, but if you have to estimate something on data and you don't have data, that's a problem, of course. So, as I told you, the Kalman filter is great for streaming data, and the problem that we're going to play with now, the pole of poles, is a typical streaming problem. So we have observation that come at some days, like random days, and we want to include that information into our estimate of the voting intentions of the people. Okay, but we usually need some initial values. So we need some observation to estimate the so-called hyperparameters or superparameters, whatever. Usually hyperparameters. I said superparameters before, but it's more hyperparameters. And if I have no data, I have to fix those in some ways, just by reasoning in some way. But something we can do that. For example, in the example we're about to do, there's a lot about reasoning we can find out by just reasoning on, because usually we know things. We have observed past even if we don't have a time series. Okay, so we can start from scratch. So you should download the data, which are I think they're called elezione or something like that. They're on the e-learning. No, they're not here. Maybe they're. Sondaggi 2024 430 si chiamano. Scaricate colissimo, vabbè, sondaggi _ 2024 430. So I just load the data, and you should do the same as soon as you have them. Maybe we will work not using all the institutions, so that we don't have to wait too long for. I mean, it doesn't take long anyway, but to be sure, my computer is really not that fast. So maybe we just select a subset of the institution that may. Oh, this is in Italian, so this is like a continental comma separated. So we have to read it using the CSV2, which uses the comma, the semicolon instead of the comma. So use the read CSV2, and you should have this. And here now we will design from scratch. We will use the Sdmtsa custom function, and we will build ourselves all the matrices from the state space form, so that once we do that by ourselves. It's a problem that is very different from the forecasting problem that we will do mostly later. But I like to do this because it needs just a very little knowledge about the unobserved component models, because here we model the trend just using a random walk, for example, as I told you. It's reasonable enough. Of course, the Gaussianity here is an approximation because these data are binomial. We're just counting. We're counting how many people are answering yes or no to the question, do you vote for this party? So if you count 0 and 1, so 0, 1, at 0, 1 random variable is a Bernoulli random variable. If you sum up a Bernoulli random variable with probability P of success is the answer yes, you get a binomial distribution, if you remember. But of course, binomial distribution, if the sample is large enough, can be approximated by normal distribution. So we know just the linear Gaussian state space form. So we will attack the problem using Gaussianity. And here, Gaussianity, of course, is approximation. We could even try harder using other distribution, but I don't want to complicate your life too much. So you have the data. So the data are pretty simple. We have the first column, which is a party. We will just select one party for our example. Then we have the date of the poll. Then we have the percentage of the poll. We have the institution that made that poll, and we have the sample size. Sometimes the sample size is missing, okay? But let's start with a simplified version of the problem. Let's at least ignore the sample size. We will then do a different example using also the sample size. So what I wanted to do, as I already told you, but actually we do a slightly simplified version of that, and maybe we complicate that if we have time. What I want to do is put so, as I told you, we have, maybe we will not use all the 40 of them, maybe we will just use 10 or whatever. So here we have the percentage for what, so I don't know, party P. Estimated by polling institutes. Okay, so this will be, I don't know, maybe we just use 10 of them. At day T, of course, or okay. Then, as we said last time, we have just one real number, which we don't know. This is the real number of votes or percentage of votes for that party. And everybody is measuring that. So everybody is, every single numbers y is equal to mu t plus some noise. So we're just assigning the same real value to all the lines, because everybody is trying to estimate that number. And this is our zeta matrix. This is, of course, our y vector. And this is our vector, state vector, which is in this case is just a scalar. It's just 1 times 1. So it's and then we said, of course, everybody is measuring the same thing, but with some noise. And so we have this vector of white noise. Let's take just 10 of them. And what about the variance covariance of this epsilon? Okay, we said actually it should be proportional to the sample size. So every single day, every single institute have a different sample size of their poll. And so that, of course, should count. But let's start with a simpler model, first approximation, then we can make this a little bit. Instead of assuming that everybody has the same precision and the difference in precision is just due to the different number of telephone polls that have been made, let's just assume that every single poll has a different precision, okay? So we assume that the covariance matrix of the vector of white noise epsilon is just like a diagonal, and everybody has a different variance. 0 other way. So we're just assuming that we're not using the polling number, the sample number, the sample size. We're just saying, okay, every single polling institution is making some errors, and the variance of the error depends just on the polling institution. We are for now we're just ignoring the sample size. Then we'll make the example more realistic and use also the sample size. But just wanted to start with something simpler. Okay. And then the state equation is just a random walk. We said, okay, we can assume that the percentage of vote of tomorrow is just equal to the percentage of votes of today. And in this time series, it's really daily. So we can speak of today and tomorrow, plus some random shock. And of course, the variance is just a scalar. It will be just the variance of each. Okay, T is just 1. So the matrix T is just 1. Okay? First of all, we have to complete, of course, the system by telling some initial values for the mean of eta at times equal to 1 and its variance. So this is a typical case where we can put some information. Of course, we can put also an arbitrary mean and infinite variance, because we can say, okay, I don't know nothing about the initial value of the percentage, but actually we know something about the percentage because it's a percentage. So we already know it's between 0 and 100. Okay, so it's something that we know. And then let's just select one of the parties here. I would say the most interesting parties are either Lega or 5 Stelle, because they are the one that moved more during the samples. So maybe just I think the example I did with Lega, so maybe we can play around with the 5 Stelle. So the initial value is about March 2018. So we will be working on this party. Can we say we know something? Okay, I don't remember much how were the numbers in that year, so 2018. First of all, it's a election poll, so no party in Italy gets more than 25%. So that's an information. Maybe 30 sometime, but I would say probably 5 Stelle in 2018, I don't know, about 20, 25, I don't remember. But we know something. We can say, okay, let's fix it about 20%. And then I use the variance to like compute like some kind of confidence interval for my assumption. So I'm sure it was more than 10%. I'm sure it was less than 35%. Okay, something like that. So we can build a Gaussian random variable where, like we said, okay, I want 99% of the probability, so this would be like 99% of the probability to be between, I don't know, 10% and 35%. We can, of course, this is symmetric, so the mean would be, devo aggiungere 12,5, mi sembra, giusto? Sì. So I can put the average at 22.5%. And then I remember that, for example, we can build interval at 99%, I think by taking the mean and summing or taking away, I think it's 2.57 times the standard deviation. Okay. So we just have to solve. So we know mu is 22.5. And then we want, for example, it's already in the middle. So like, okay, so we have just to solve this. And we have the sigma that is providing us exactly the expectation I just expressed. I want something that is with 99% probability between 10 and 35%. And so this is just 5 minus 5 divided by, is that right? So we can compute that. I mean, it's approximated. It's not important to be precise here, but just to give you kind of reference on how to generate initial value. So that would be 12,5 diviso 2,5, facciamo un po' più di... Cos'è? Circa 3, 4. Facciamo 4. Ok. So gli mettiamo anche 5, facciamo per fare I numeri tondi. So just to round up, like let's just put a standard deviation of 5. This is just the initial value, but it's more reasonable than putting an infinite variance. We know something, we can express our knowledge using a probability distribution and give some information. Yes? No, I just reasoned about my memory about Movimento 5 Stelle in 2018. No, it's not random. Otherwise, if I want to express my complete ignorance, well, I'm sure that in 2018, Movimento 5 Stelle was more above 10%. I'm sure, just by memory. Yeah, probably years younger, so you don't remember that. But at my age, the time is all compressed. Things are not more so back in time. So yeah, I think in 2018, I'm pretty sure it was more than 18%. I mean, we can cheat. We can also look at the data. So maybe it was wrong. I mean, prior distribution can be wrong. It was 34.5, at least according to SWG. So I got the right range, but it's not centered on my memory. So my memory was actually probably was the maximum that Movimento 5 Stelle. Yeah, actually 2008, 18, 2017 probably was the election where they got the highest. Yeah, it was just because before COVID, 2018, 2019. Yeah, they were at the top. So my memory worked badly, but so we can fix that as well. We can. Okay, I changed my prior distribution. This is more a likelihood to observe a number. So we can move that a little bit more up. So I would say we can keep like 5. This is a very large uncertainty, but maybe we can put the average to 30. Okay. Okay, 25. But anyway, it's not that relevant. I mean, that number will be important for the very first numbers that we're estimating. But then the system will have enough data very soon to just forget my initial guess and just use the data. So you can also start with the infinite variance. You will see the only thing that it changes is the first few initial guesses. So, but anyway, we can also start with my wrong guess. Let's just stick to my wrong guess. Okay. This is the average, and 5% is the standard deviation. Okay. It will work. And that's it. So what we have to estimate are just all these variances, because now I'm assuming that every single polling institution has a different precision, and I'm just skipping the sample size of their interviews. And then we have the variance of the evolution of the of the intention of votes for 5 Stelle, okay? So let's try to transform this into a state space form. Actually, it's already in state space form. I gave you all the matrices. Now we just have to move to class. So this. Now, first of all, we have to prepare the data, because of course the data are not yet they're not time series yet. It's tidy data. This is like a tidy data representation of the information. First of all, we want to extract just one party. In our case, we get the M5S, so M5S. We want to select maybe less than the 40 polling institution. We'll just get maybe, let's just maybe select the 10 polling institution with the highest number of polls. So we can count in this period of time how many polls every institution has made, and we keep the 10 that have the highest number of polls. That could be a good choice. And then what we want to do is making a wide data set where there is one column for every polling institution, there is a column for the date, and remember that we don't have polls for every single day, so we have to generate missing observations for dates that are not present in the data sets. So there are some elaboration we have to do on the data, some wrangling. But as I told you, if you use the tidyverse word, everything will be relatively simple. So this is loading some of the packages. Okay, so first of all, let's just decide the polling institution we want to work with. So let's just count how many polls they have done in this period of time. So we can like group by institution, which is called Istituto, I think. And then just summarize by counting. So for counting, this is the function. This will just count how many observations are in each of this group. We can first, well, we can put that into a new data frame. So we can call it actually, we could sort it already. Okay, we can sort it and keep the first 10. So as you see, there are like institutions that just have like 5 or 7 polls. That's not very informative. So we can take the first 10 and they all have hundreds of polls. So just to make the code readable, institutions to keep. So we let's make one more step here so I don't have to do that here. We can arrange in ascending order, in descending order, based on n. This is now sorted. You see, it's now sorted, and we just pull out to extract a variable. We can just go with pool, or we can extract it this way. I mean, it's the same thing. And we want the first 10. Okay. So these are our institutes that we want to keep. Okay. Just to work on a smaller, we could work on all 40, but I don't want to wait too much. Good. So what we need to do now is, first of all, is selecting the party we want, selecting the institutions we want. I would also build like a time series of dates with all the single days between the first date present in the data set and the last date present in the data set, right? Because we want to create all days. All days. We want a daily time series, even though many of these dates will be missing, okay? But missing observation, as I told you, is really not a problem, okay? So I would create like a helper variable. We can call it date. And I would call, we can generate a sequence of dates. Yeah, we have a problem. First of all, we have to deal with the problem. The date here is not a date, but it's a string. You see it. So actually, first of all, maybe it's a good thing to turn this data, so this date, into a date. And let's do that before doing this. Actually, maybe, well, let's do it here. We can do this using tidy word, the tidyverse word. So day data is equal to as date data, and then we have to pass the format, because of course it's let's say the Italian or a continental format. It would be the format like percentage day, so percentage d, sorry, slash percentage month, slash percentage year in four, I think it's four figures, yes. So large Y. This is a way to communicate the formats of the date. Of course, we could have also tried other automatic recognition things, but I mean, I'm sure this is working, so I don't want to carry risks. And we overwrite the same data set, okay? Okay, now it's a proper date. Now, let's go back to, are you following me? It's not complicated, but I mean, I never know how acquainted you are with this tidyverse world. So if you have problems, just stop me. I mean, we have a lot of time. We're in lab. There's just few students, so I can just also come to you if you have problems and help you solve them. So we can, for example, take as a starting date the minimum from data. So just to show you, of course, the minimum works also on dates. So this is the first dates in the sample. And of course, we can also take the max, and that would be the end. If you want to have more explicit names to what we are doing, we can write this like from to, so maximum date. And then by, the nice thing is that we have so sec is actually a generic function. There are many sec functions. If we use a date as a first argument, then that's the sec date function, which generates a sequence of dates. And the by is just the name of the distance between two subsequent dates. Here, actually, it would have worked also just by summing, just to show you. The internal date format of R counts the days. So if I sum 1 to this date, I get the next day. And if I produce like a vector of date, so this would have worked as well. Okay. Anyway, so we have actually many sample points, so time series points. We have more than 2,000 observations, or some non-observations. And now we have to restructure our data set, because as I told you, we have to select the institutions in the party we want to work with, and then we have to put the institutions on the columns, so on the fields. And so let's start with the extraction of the part of the data set we are interested in. Well, so first of all, let's filter the data. We want partito equal to M5, no, M5S. And then we want istituto belonging, so there is this operator, it's a match function, instu_keep. So the institutions that are in this vector of institution that we just created. And I think the filtering, so the where statement ends here. Then we have to select some of the variables because we're not interested to all of them. So the partito, for example, we are not interested because we just have one party. The date we are interested in. Percentuale, we need it. And istituto. And campione, so the sample size for the moment we don't want. So these are just the three variables. And then we have to now reshape so make the data wider. And we can use the function pivot wider. So the columns that have to be made wider but we can write, so we can write names from, so we want the name from Istituto and values from percentuale. I think if I'm not indicating the variables, maybe it takes all of them. I never remember exactly. But anyway, let's see if it works. Well, we can start to see if it works, and then we will add also the missing dates, because we have to add also the part on missing dates. This is just a trial. Oh, actually, we can just view it. Oops. So partito, probably I did something wrong. Oops. What's the problem here? This is a new error. I never saw that. It just printed. Ah, okay. So I'm probably I just misspelled something. Percentuale. Ah, data. Giusto. Okay, here, sorry, I think we should. Sorry, here, I think we have to add also the dates. We have maybe just to select this. Oh, no. Now it wants, I think it. Sorry. I'm messing because they changed a little bit how pivot wider works, and I haven't yet made my mind right. What I'm getting wrong is can select columns with try that this way. No, it's not working. I think maybe ID calls. I know, I know. I don't know why I. I don't know why it's not working. What's the problem? It doesn't like dates, but A te funziona? Sì, no, infatti io l'avrei usato così. Allora, vediamo che errore mi dà. Istituto. Ah, it's a warning. Ah, it's Johnny only warning. Sorry. Let's go to view. Okay. No, it's working. One thing, we don't want null here. We have to specify we want NA, so missing observations instead of nulls. Okay, so that's one point. And I think there's a way here to indicate the value fields, for example. Yeah, so values field, we can just fill it up with NA. Otherwise, it remains null, which doesn't mean anything. So values field, we put an NA. And this is actually null. Why null? I mean, I did the other example. I didn't have any of these problems. I don't know why. I mean, let's look how I did it. I just don't remember. I didn't do it recently, so I'm sure I did something similar here. Okay, probably that's the problem. Yeah. Well, this is there. I mean, this is correct. This is what we are doing. That's why it's not working. Now I remember why. We didn't consider the possibility that actually one institution is doing more than one poll in the same day. I think it just happens maybe once or twice in the whole data set. But of course, the function doesn't know how to, because of course the data should be unique, doesn't want to repeat the date. And so we have to provide a function to summarize the percentage when there are more than one polls in one day. And that's, and this you can do using this values function made. All the rest, as you see, is the same. So I don't know why having so many problems. Okay, well, let's add that. I didn't think of that. I think also last time I had to think long to understand what was going on, but I'm not sure this will fix everything. So the values function, values function, and we take the mean. So when there's twice the same value, we take the mean. And this is terrible. I don't know what's happening. Select that. So you get also the same problems that I have. No, now I have a lot of problems because I get only NAs. A voi funziona? È veramente strano sta cosa.
Sono molto variabili.
A me è identico a quello che ho fatto. Vabbè, il partito è diverso. Avevo fatto select escludi al posto che includi. Beh, stavo usando le altre pipe, ma non penso che questo sia. Mm. Dici? Mm.
Magari scrivere nell'environment.
Ah, dice di tutto, facciamo una roba stile Microsoft, controlla il cancio, diciamo. Ah. Beh, se funziona però è terribile. Poi, a parte che c'è questa regola che se qualcosa può andare male mentre fai la lezione, succede. Sì, sì, durante la lezione. Cose che hai provato 12 volte. Magari è vero anche per gli esami, non me lo ricordo più, da parte mia. Cioè,
Per l'esame,
anche per l'esame. Stai mettendo le mani avanti.
no, nel senso che agli esami se i computer si possono rompere, si rompono. Se si può bloccare il sistema degli esami, si rompe il computer. Perfetto.
Un nuovo errore che non c'era prima. È strano. Eh no, guarda, è uguale. Allora, cerchiamo di capire che cosa sta andando male. Però è strano, sono gli stessi dati con le stesse cose. Mm. Ah, non gli piace... Questa volta non gli piace il view. Strano, però. Vabbè, mettiamo famosa foobar, famose variabili. Cos'è che vuole senza parentesi? Sì, no, senza. Mm. Ok, il foo sarà come prima, immagino. Sì. Vediamo i warnings, cosa... Cioè, a te sta funzionando? Ragazzi, come fa- non so che cosa sta succedendo. Aspetta, non è che ho roba non numerica dentro di T? Beccato, ecco l'errore. È un char. Ci sarà qualche cavolata dentro. Mm. Il vostro è numerico.
Dipende se l'hai importato con CSV col punto.
Avete usato l'underscore o il punto?
Io sul file, sulla lista di file aspetta che importo la passetta importato.
Io ho fatto normale mettendo
Però, ah sì, perché giusto, ecco perché. Allora, il separatore è italiano, ma il numero è invece in notazione anglosassone. For those who are watching TV, so the problem is that we have a string here, and that's because we have a separator of the field, which is, let's say, the continental version, but the decimal separation is made by like Anglo-Saxon standard. And so that's why your solution solve everything. So this solves because we just indicate set. Right. Otherwise, we could have done also as numeric and it would have understood everything. So that was the origin of all problems. Sorry about that. I mean, but it's nice to solve problems like together. It's very sparse. I mean, there's really a small number of samples. But as you can see from here, it's not sparse enough because there are a lot of missing dates. So, for example, between the 15 and the 19 of March, there is nothing. So we have to add the missing dates. Why do we have to add the missing dates? Why do you think we have to add the missing dates? Couldn't we just work on not evenly spaced data. What is the problem, you think? Why I'm insisting to put all the missing dates?
Otherwise distruggiamo il concetto di soluzione.
No, non tanto per quello. Because we are assuming that the opinion from one day to the next move with a given variance. So if I have some observation that are every day and some observation after 1 month, of course I had much more time to change my mind in 1 month than I had in 1 day. And so the variance between the observations with 1 month of distance will probably have a variance which is 30 times higher than the variance between the 2 days. That's why we could fix that. I mean, in this case, we want to produce every day because my say my committant was asking me for a daily indicator of the percentage of votes. Okay, and so I want daily indicator. Actually, I could even just fix the state space form and just leave the dates as they are by just saying that the variance of sigma eta is proportional to the number of days that have passed between this observation and the previous observation. So I could have managed that differently using state space form, for example, but it's much more easier. And also because in this case, it also answers to the question, I want a daily indicator of the percentage of votes. So we can just add one more step here. And the one more step is the left join, no, actually right join of course, dt, and then I have to produce a data frame. We can call data, so use the same name, and just put the dates we generated. I don't even have to define the join variable because it's got the same name, so it probably will understand it by itself. And maybe now I will call this like working data, so WDT, working data. And we have an error. What's the problem here? Sorry, here's, I put a useless comma. Okay, it worked. So it understood by itself that was the date. So now the working date, so it's here, it's exactly what we want. We have the dates here, and the dates, of course, then we have just to throw away when we work with the state space form. We don't need this. And we have this very sparse matrix. Well, no, the dates are still missing. Sorry, what's the problem here? So I did the right join. Actually, the right join should keep all the dates here. So why it's not working? Do you have any clue? 14, 15, 19. Because no, maybe I have to say that that I have to create missing observation. So yeah, I have to supply information for missing. Let's check how I treated this. Actually, I did the left join, changed the order of the data sets, but actually it should be equivalent. It's strange that the right joint doesn't work as a left joint. Change. Well, if it likes how it treats the missings. Oh. Ah, brava. Vedi, tutte le robe che possono andare. Allora, ok, so allora we can arrange date, data. Okay, thank you. So you have me solve all these problems. That's good. But then there's a partito again. What's the problem here? I opened the wrong one probably just. Okay, great. Now we can work with the state space form. Good. So the data now we have. Let's start just designing the matrices, and then we will use the SSM custom to build the state space form. So first of all, let's build the easy part. I don't want to overwrite over T, which is also for true. So I always use matrix T or matrix Qs. So what's matrix T? It's very simple. Matrix T is just, it just contains, actually, well, we can pass the matrix. It's a 1-by-1 matrix containing 1, okay? So, because we just have one state variable and it's a random walk, okay? What about the Q matrix? Again, Q is, so Q is the variance covariance of the disturbance error, disturbance variance of the state vector. There's just one, and we have just to put the sigma eta. We don't know the sigma eta, fine, let's just put an A. Maybe it's put, to be sure it's in a number, I put an A real, just, I mean, if it's just an A, I think it's assume it's a number, but to be sure, just. So NA, because I don't know it, I could put also an arbitrary number, but I put an NA, I'll tell you why this is a good choice. Then the starting values for the mean and the variance here. So we said in my resemblance, which was wrong, but anyway, of the votes of Movimento 5 Stelle, I said, okay, let's put initial value of 22.5. Okay. So this is just actually it's a matrix of 1-by-1 because there's just one state. It's always a column matrix, so a column vector. But here it's also a one row because there's only one state variable. I want to give also an initial variance. Again, it's 1-by-1 in this case. And we said maybe 5. Actually, 5 was the standard deviation, so the variance is 25. And remember, we have to also inform that we have no infinite variances. And so there is also this P1 inf. Remember, the P1 inf is just relevant what's on the diagonal. And of course, this is 1-by-1, so it's all diagonal. And if it's 1 is infinite variance, if it's 0 is finite variance, okay? And so this is all that is needed as far as the state equation. And then the observation equation, we just have to define, well, here I'm missing the M, but it doesn't matter. Zeta, so what's zeta? Well, zeta, if you remember, is just a column of ones here, because it's just selecting the only state variable, and it's attributing to all the observations. So we selected 10 institutions, so we have just 10 metrics of 10 by 1. So it's all ones, and it's 10 by 1. And then we have finally the variance covariance matrix, which we usually call H. It's a diagonal matrix because we are just assuming, if you remember, this is our H. So we just want zeros out of the diagonal. Why zeros? Because we're saying conditional on the fact that they're measuring the same value, but the errors they commit in measuring that percentage is not correlated among institutions. Okay, that's an assumption which is reasonable. And then the other assumption we're doing is that we said, okay, we assume that every single institution has different variance. And we're at the moment missing the part having to do with the number of interviews. Okay. So my suggestion is just repeat a real missing observation by 10 times. And so this is just creating a matrix with a diagonal of missing observations. Again, there's a good reason to putting all these NAs on the diagonal of H and also of Q. And that's because there is actually a default function, a default update function in R, in CFAS, to work for this situation. So we don't have to write the update function for this case. Maybe we should as an exercise, but at first base, maybe we can just skip it. One more thing. This default update function, remember the update function is the function that takes the unknown parameters that we pass through a vector. In this case, how many unknown parameters do we have? There's just 11 because there's 10 variances here, 10 variances, which is the mistakes every single institution is making. So that's variance. So 10 plus 1, the one which is the variance that tell us how quickly people change mind or vote intentions every day. So eta, the variance. So 11, we have just 11 variances. So we will have a vector of 11 variances, and we have to pass that to an update function. The update function has to take those 11 variances and put it into the right places in the matrices of the state space form. There is one problem, of course. The optimizer which is implemented doesn't know that there is a variance and that a variance has to be non-negative. So how do we solve that problem? So the optimizer doesn't know the meaning of the parameters we are passing, okay? And variances cannot be negative, and we don't want the optimizer to try negative variances. Otherwise, it will throw an exception, an error, okay? So how do you think we can solve this problem? Well, penalizing could be a solution. But sometimes the problem is that maybe if the common filter encounters a negative variance, it just throw a mistake, an error, and so you're not able to penalize I mean, you can, yeah, okay, you can define the objective function, checks, but we're not, in this very moment, we're not the ones that write the objective function, because we will be using the fit SSM function that does that. Of course, there could be a solution. Yes, he provided actually a good solution in general. There's another trick, and that's the trick we usually use in many of these situations. We change the parameterization. Instead of parameterizing by the variance, we parameterize by the log of the variance. What does it mean? Well, if that, then we have to take the exponential to get back to the variance. And so if we pass any number and then we get the exponential of that number, the result is a positive number, okay? So the idea is that we don't reason in terms of variances, but we reason in terms of log of variances. And that's exactly what the default update function does. The default update function, as I told you, will assume we just want to estimate variances, which are found, of course, on the diagonal of the Q and H matrices. But it's assumed that we're passing the parameters in this order. First, the NA of the Q matrices, the Q matrix, and then the NA in the H matrices. So the order is that one. And all the variances are actually log variances. So we will take the exponential. And that will assure that every tried variance is actually a positive number. So that's a trick we will be using. Sometimes we will use just the exponential to make number positive. We could also take the square. I mean, the square would do the same. Or alternatively, we could, if we have to like fix a parameter in a given bound, sometimes we have to do with parameters that have to be between 0 and 1. And in that case, you can take, for example, the logit function. So the sigmoid, whatever you want to call it, that keeps numbers between 0, 1, or any two numbers. So that's a trick we will be using. Anyway, so for the moment, we can just avoid of writing the update function. First of all, we have to produce the model. We can call it model 1. The constructor is called SS. Of course, we have to load the fast library. Model. Okay, as you see, it wants a formula and possibly the data, but actually we will not be using the data. Yeah, I mean, we don't have to use the data. So we can pass just the data. Our data are WBT. We can just throw away the first column. The first column is the dates. We don't want that. And then I need a tilde, of course, which I don't have on my keyboard, so I have to steal it somewhere. Here. And we will be using, well, 0 because we don't want any intercept in this moment. And we will be using SSM custom. If you look at SSM custom, which is here, for example, it just wants the matrices in this order. Or let's just look at the right place. SSM custom. So with SSM custom, we build freely our state space form. So first of all, zeta, which we call m zeta. Then we have t, which we have called mt. Then we have the r. The r, we didn't define the r. R in this case, again, is just 1 by 1 equal to 1. So let's just build also the r. I forgot the r because in this case, it's really useless, but we have to build it. Oops. Sorry about that. R. Then we have Q, which we call MQ. And then we have A1 and P1 infinite, which we call the same way. And the rest doesn't really matter. We could even give a name to the state variable, but in our, I mean, we could call it level if we want to. It doesn't really matter. Let's just leave it unnamed. And then we have to put outside of the formula the value of h. which we called MH. So in practice, so here we define the state space 4, but for the H matrix, which is extra parameters. There are good reasons for that. Good. It doesn't like, it probably just want a matrix here. Yeah, what's the problem here? Maybe the dimensions. Dims. Actually, it's correct. Maybe we should cycle. Sorry, I got it wrong. I didn't define it. Okay, it's working. Sorry, I for some reason I selected SSM cycle instead of SSM custom. Okay. Okay, so this is correct. Okay, the model object is rather complex, has many things inside. Of course, an object in R is usually in S3 is just a list. So we have the data, we have the metrics. Actually, if we look at the inside M, so for example, if you look at the zeta matrix, as I told you, it is now actually a three-dimensional array. Inside, it always use the form of a tridimensional array, okay? And the third dimension in this case doesn't change over time, but it's there, okay? Well, the name of the variable is just custom. We could give a better name, for example. We call it mu, we could call it mu. Just to give a friendly name. State names. State names. Now we just have one state and we can call it mu. In our formula, we could have mu, so it could be a good idea. So this is the zeta matrix. There's one state variable that every single institution receive as it is. So, and then of course there's the H matrix, which is the, of course we don't know the variances, we have to estimate them. So it's all made of NAs. And the T matrix is very simple. It's just one by one. It's just a random walk. And Q is missing. Okay, now we're able to go a step farther. So estimate the variances that are missing. The problem, we have to generate initial values for the variances because in numerical optimization, we have to provide initial values. We can reason about initial values. They're just initial values. Then they will be, of course, changed. We can call that init. And of course, it will be the log of the variances. And we can, so there are percentages, they're making mistakes. I don't know, we can think every single institution to make mistakes by, I don't know, 3-4%, maybe less than that. It's just a starting value. So it means like, of course, we have to pass the variance, not the standard deviation. Remember, if you want between 2 times plus and minus 2 times the standard deviation, that's 95% of the distribution. So we can, if it's go, we can put a starting variance of, I don't know, So 25, so 5 times, it would be 2.5% twice, so 5% squared 25. So we can repeat that 10 times, but actually first the Q and then the H. So that would be the H. The Q, that's how much we change our minds every day. So probably that would be very tiny. So a variance here, I would put a small variance, maybe 0.1. So we have, this is the variance of beta, and this is the variance of all the epsilons, okay? And I take the log because, as I told you, the update function will take the exponential. So these are just initial values. We can call this fit1, and we run the fit SSM. We pass the model, which we call M1. We pass the initial values, which we call init. In this very case, we can also skip the update function, because the update function, we can use the default, because there's just variances and there are NAs. And now it's estimating the model. What's inside fit1? There are two things. One is the output of the opt-in function. So if you know the opt-in function is just the output, the opt-in function. So these are the parameters at the value of minimum. Actually, it's minimizing the minus the likelihood. And this is the values of minus the likelihood. Of course, these are the log of variances. In order to obtain the variances, I have to take the exponentials. And this is the number of times that the function was called. Actually, I think we reached the maximum number because by default, I think this method has 500 iteration. Convergence, if it's 0, we're happy. If it's not 0, there are some problems. And the problem here is that we reached the maximum number of iterations before converging. We can either just don't care. I think we're pretty close to the optimum anyway. Or sometimes we can even change the method. I usually use the FGS method. Actually, it converged in much less iterations. So the BFGS is usually the one I suggest to use in this situation. Okay, but we can also change the maximum number of iterations. Okay, and the other thing that you find inside here is the model. So another state space form, but this time, for example, if I look at Q, I have the variance. And if I look at H, I have the covariance matrix. Ok? Ma voi avete tutte le lezioni? Ah, okay. Vabbè, cerco perché vedo che vanno via tutti. Il messaggio è chiaro. Dovete dirlo magari prima. Però un po' vedo che hanno altre lezioni, ognuno avrà lezioni un po' diverse. Well, let's finish this example. So now we have a fully usable model because we have no NAs inside the state space 4. And this is about the errors that the institutions are making. It looks like some institutions are more precise than other ones. For example, the first one seems to be much more precise than the second one, for example. Or the last one is also more precise. So they kind of have a smaller estimation error. Maybe they have larger average sample in their questions. And what about the variance that we change mind every day? It's a very small variance, okay? We don't change mind very quickly from one day to the next. Okay, so now we have the model with everything we need to use it. what do we want to do? Well, we want to extract this daily estimate of the number of votes, or the percentage of votes. Now we pass the common filter and smoother. We can like call this KFS1, for example. There is this function called KFS. We have to pass the model to this function. So we have mod one, fit $1 model. This is the estimated model. And then as you see, there's the filtering and the smoothing. There's more than one possibility, both in filtering and smoothing. Let's just start with filtering equal to state, so the state variable, and smoothing is equal to the state variable. Let's run this. So now we have passed the common filter. So the common filter is the real time estimate of in this case, the percentage of votes based on all information available at time t. And the smoother instead is the best estimate of the number or the percentage of votes for every day based on the whole sample. So one is a real-time, so streaming data estimate, and the other one is an estimate using the whole sample. That's the difference. Let's just look at those. So we can, of course, we can make nicer plots, but let's just produce maybe the. Okay, inside the KFS, it's full of things. Okay, you have to. So this is the filter. So APT, if you remember, we use the same name for the filter, and this is the time series of covariance matrix. So we also have uncertainty about that. And this is usually a vector, but we have just the mu. So in this case, it's just one. It's not a matrix. Now it's just a vector. So this is the filter. Maybe the filter I think it's already as a time series. So let's just change the color to maybe the filter. I make it blue. And this is the real-time estimate of the number of votes. Probably here there was an election, so there's a sudden change in the. And this is the smoother, which is it uses the past and the future. So not only the past, it's called alpha hat in this case. We will, of course, then say something about the KFS function later. And it's not very different, just a little bit smoother. So this is like the time series. One is a real time, the blue one, the red line is ex post. So using all information on how the percentage of votes. Of course, there are no dates. I'm not using the dates. We could do a better plot. I will provide you with a better plot later when I load this on the e-learning. But this is the best estimate based on all the information, all the polls. As I told you, the blue line is based only on present and past polls, and the red line is based on all the polls. For example, you may notice that the red line, the blue line here moves by jumps. Probably here there was an election, and you know that there's a period of time, I think 1 week, in which you cannot do polls or publish polls in Italy before an election. I think this is the European election of last year. And as you see, the best estimate doesn't change for a week. Of course, if we have no new information about about the state variable, we're using a random walk, and the best estimate of the random walk, if I have no information, is just the last observation. So you see that the filter here stayed constant for a while, and then probably we have the first pulse going on, so have some jumps here and go up. So probably this was the estimate before the election, and we have the election here, and after the election there is a jump. And of course, the red line that sees the past and the future is this up with a continuous line, okay, somewhere. And probably here there was also an election. Probably I should use it. So here there was an election, here there was an election, because you see that the filter remains constant because probably there's no new pole here, and so it just stay. And then of course after the election usually we have jumps, because I don't know if it's the poll institutions that change how they produce the data, how they correct the data, because poll institutions actually correct the data before. Because there are many reasons. We had sometimes seminars about that here made by famous poll institutions. The problem is that when you have two problems when you do polls. First of all, you have not the same probability of getting somebody to answer for every party. So the percentage of votes for that party is not independent of the number of answers you will receive. And probably, so there is a distortion because sometimes for people that vote at the extremes, it's harder to answer to that, and so they don't want to answer to the polls. And so you have underestimation of extreme parties usually. And that's one problem. And the other problem is sometimes, well, it's actually a similar problem. Sometimes the people that you call would answer honestly if they're alone, but sometimes they get called and they're not alone. And so they don't want other people to know maybe they're voting an extreme party or something like that. And so you have a bias in the estimation using on a downward estimation of extreme parties. And so with their experience, they have like coefficients to correct this. But sometimes like there are new parties and so on, so you don't have an experience for correcting that new party. And so, and of course, after the election, probably they change all these coefficients, because you always see that polls change just after the election, and they get more coherent with the elections. So that's probably they're changing their correction coefficients. And another thing that they told us is they actually big institution, they call each other. They kind of compare their results and they adjust the results to each other. So they're not really independent, because I mean, they probably call each other and say, I have this number, is your number close to that? Why my number is, so I don't know. That's something that was told to us by some of these institutions. But anyway, that was the exercise. Of course, if you go to the R Markdown that it's published, I do a better work. I mean, it's more complex. I keep track of the estimation of sample, as you see here. So the variance of the epsilon, we assume it's the same one for all institutions, but then we divide by the number of interviews for each poll for each institution. So that's the difference. Well, this is just a way to explain how to get initial values. And yeah, the rest is very similar, but here, of course, there is a update function, which we didn't define. And here, the update function, you see, I run a for loop over the variance of H, because we have like a common variance divided by the sample size, which I pass as a further parameter. But anyway, you can kind of look at this example. This was made for Lega, and here I also put the original data. So this is the value of Lega over the time. So the poles are around, and of course, and here you see clear, this is the smoother. You see the smoother because it goes down really smoothly. But here there were the European election. So the poles were here, and then suddenly they adjust to the new level. Well, there are some poles here. The very polls that were very close to the elections were already registering this trend. Here, there's the pause probably, and then it starts again.
Comunque, sono le politiche queste, non sono quelle del 22.
Ah, le politiche, hai ragione, sì. No, sì, giusto, perché questi qui i dati finiscono prima delle europee, perché me li hanno dati proprio per le elezioni europee. Infatti finiscono un po' prima, penso un paio di settimane prima delle elezioni. Hai ragione. Sì, le politiche. Anyway, you can check this. I mean, this is much more complete. Okay, let's stop here. I guess I have to keep in mind that. Sì, certo. Sì, questo è bruttino perché. Sì, okay. Inside this new object, this Kalman filter smoother object, the filter is called ATT. We call it AT given T, if you remember. And we call actually the smoother AT given N, but here it's called alpha hat. So this is usually a matrix because we have more than one state variable. Here we just have one state variable, but usually we have many state variables. And this is also a matrix with the same dimension. I also have one step ahead prediction actually inside. There's a lot of information. And the nice thing is that, as you know, most of this data are missing. So missing observation is really not an issue. We are using the information that there is. So this is our initial data set. It's really most of the observations are missing. But we're using like time information and cross-sectional information at the same time to provide always the best estimates. So we're like doing the best use of any information. Outside the state space realm, this would be very, very complex to use. And in the state space realm, if we're building a credible model, so a model that catches all the features of the data generation, and here we are not, because of we are not using yet the number of interviews, but we are producing the best possible estimate, of course, in a square loss function, so the best mean square error estimate possible that we can base on this information and on the model. Okay, and this, as I told you, would be incredibly complex to do outside the state space form. So it's very powerful. That's why I wanted to show you this example, which is kind of different. It's not the usual, I want to forecast some time series. This is, I mean, it's a streaming data example at the end. In fact, I provided the firm that asked me this work a Shiny app. They had just to load up the new data set, and the Shiny app was communicating with, it was not, I don't remember, it was one of these platforms you can make graphs with data. I don't even remember the name, like Tableau, something like Tableau, but it was not Tableau. It was, no, it was not Power BI. But anyway, there was an API, and R had this API to communicate with that system. And so they just needed to provide the Shiny app, which I think is still on, with the new observation they had. the Shiny app would do all the computation and will send the new plot to this data wrapper or something like that. And so it was actually streaming. It was manual streaming because of this data were generated by and gathered by some human being, but the rest was really some streaming. And I think you can still find it on the web or something. The firm it's called WithHub. Ah no, era in italiano, poi stupido, lo scrivo in inglese. Sondaggio dei sondaggi. Arrivederci, eccolo qua. Dov'è che è? Ah, è questo, sì, ci metto un po' di... Forse no, forse non esiste più. Ah sì, eccolo qua. Bello. Ah no, sì. Ecco. Sì, avevano selezionato alla fine solo 5 partiti. Vabbè, poi finisce prima delle elezioni. In realtà potrebbero benissimo farlo andare avanti, perché il sistema è ancora in piedi. Vabbè. Sì, l'avevo fatto con Gianna, perché Gianna aveva il contatto con loro. Vabbè. Okay, we stop here. Zac.